Assalamu alaikum. In this video I'm going to show you how to determine the critical angle of light in a transparent medium such as glass or perspex. Now the critical angle is simply the angle of incidence in a medium for which the angle of refraction turns out to be 90 degrees to the normal. And this only works when light travels from an optically denser medium such as glass or perspex or water into an optically less dense medium such as air. And the reason for that is that when light travels from an optically denser medium to a less dense medium, it bends away from the normal. And this only works when light travels from an optically dense medium to a less dense medium. So this is the only scenario in which light, as we increase the angle of incidence, the angle of refraction would go closer and closer and closer to 90 degrees. To conduct this experiment, we require a ray box, which is our source of light, a power supply to power up the ray box, of course, a single slitted filter to produce a single ray of light using the ray box. Ideally, you should be using a thin slitted filter rather than the thick slitted filter, so that the beam of light or the ray of light is narrow enough not to overlap multiple degrees on your protractor. So let's begin. We power up the ray box and the ray box produces a single beam of light. We're going to use a semicircular perspex block, although we could have used a semicircular glass block or a rectangular glass block or a rectangular perspex block as well. And the reason we prefer to use the semicircular block over the rectangular block is that because the surface of the semicircle is curved, therefore the normal, which is drawn at 90 degrees to the tangent at this circle or of this curve, would keep varying as we shift the ray box from one position to another. And in that sense, what we'd managed to do is essentially, we'd managed to shine the ray of light at an angle of incidence of 0 from the air to glass boundary. So as light travels from air into that glass, the angle of incidence would be 0 degrees. The ray of light would travel along the normal itself. And therefore, there would be no refraction, there would be no change in direction of light as it enters that glass block or that perspex block. Now, in contrast to that semicircular glass block, if we used a rectangular glass block instead, well, as we changed the positions of our ray box to change the angle of incidence, the light would strike the air to glass boundary at different angles of incidences. And that would imply that the angle of refraction in light would keep varying, and that's pretty hard to control by simply moving the ray box across, right? So that's why we prefer to use a semicircular glass block, although it works for any geometrical shape. Right, going to start by placing the semicircular glass block on a sheet of paper. Let's remove the ray box for the time being and use a sharp pencil. A sharp pencil is required to improve the accuracy of your experiment. Of course, you've got to look at the lines that you draw or the positioning from directly above in order to avoid parallax error, of course, right? So you can't be looking at the things you draw at an angle. And you take your sharp pencil and you draw a boundary around your glass block. And the reason you do this is in case that semicircular glass block gets moved or replaced later on, you can put it back to its original position. Because remember, in an experiment, you're only allowed to change one variable at a time. Right, so here's the glass block. I've got a printed protractor to help me out. Although, what you could do if you've got a physical protractor is use a pencil to mark a point somewhere along the center of that flat surface. This is where you're going to point or shine your ray of light, okay? And draw a normal to that point, to that surface, using your pencil and your protractor. So the normal must be drawn as a dotted line at 90 degrees over here, right here. So 90 degrees to the surface. Now we place the ray box in such a way that the angle of incidence between the air to glass or perspex boundary is 0 degrees, because the incident ray travels along the normal as it enters the glass block. And because the angle of incidence over here was 0 degrees, the ray of light doesn't bend and it carries straight on. At the glass to air boundary, or perspex to air boundary, the ray of light is again traveling at the normal, along the normal. So the angle of incidence is 0 degrees, and so the angle of refraction, the angle between the normal and the refracted ray, is also 0 degrees. So in other words, the ray of light carries straight on. Now, as we increase the angle of incidence just a bit further, so here's 10 degrees, you see that the angle of refraction, so the angle between the normal and the refracted ray, is greater than 10 degrees, it's 15 degrees. So the ray of light bends away from the normal as it exits the glass block. And also note, as the angle of incidence increases, a faint reflected ray, a partially reflected ray, starts to appear along the other side. So that ray of light is basically being partially reflected by this glass to air boundary. It's not totally reflected yet, it's only partially reflected. And we keep increasing the angle of incidence. So here's 20 degrees. And note how the angle of refraction this time is 30 degrees. And when the angle of incidence is 30 degrees, the angle of refraction is 10, 20, 30, 40, approximately 50 degrees. So the angle of refraction is always greater than the angle of incidence inside the glass block. We're looking for the angle of incidence here for which this ray of light travels at 90 degrees, meaning scrapes along the boundary of the glass block. We're looking for the angle of incidence for which the angle of refraction is 90 degrees to the normal. Do note, as we increase the angle of incidence, the partially reflected ray gets stronger and stronger and stronger, until a point comes where the ray of light is scraping along the boundary, so you can only see the red colors refracting out. The rest of the light is refracted in. This is the point at which the angle of incidence is equal to the critical angle. So the angle between the normal and the incident ray at this point, the angle of incidence for which the angle of refraction has turned out to be 90 degrees, is known as the critical angle. In glass, this angle turns out to be approximately 42 degrees. If you were using a thin slitted filter, this ray of light would be much thinner, and you'd be able to clearly read the actual angle of incidence rather than having this thick ray that covers a range of degrees, so it's difficult to predict what the real angle of incidence is. So that's one way to improve this experiment as well. Now, beyond the critical angle, the ray of light can no longer refract. There is no more room for the ray of light to refract back. So in this case, the ray of light starts to reflect back inside the optically dense medium. So the ray of light starts to totally internally reflect now. See that, notice how none of the light is being refracted out now. This is when total internal reflection occurs. There are two conditions for that. The angle of incidence must be greater than the critical angle, and number two, the light must be traveling from an optically dense medium to an optically less dense medium. And so now, because light is reflecting instead of refracting, it no longer obeys Snell's law. Instead, it follows the laws of reflection. So this time, as the angle of incidence, as the angle between the normal and the incident ray increases, the angle of reflection increases along with it. So angle of incidence is equal to angle of reflection. Right? So this is total internal reflection. If you were asked to determine what the critical angle of light was, you could use your pencil to mark 2 points along the incident ray, so that when you remove your glass block and your ray box, you'd have a ray of light to draw using your ruler all the way through to the point at which you were shining your light, which was the center of your flat surface. And so you could use your protractor later on to determine the angle between the 90-degree normal and your incident ray. Now, total internal reflection doesn't only occur with semicircular glass blocks. So as I said, the critical angle of light in glass is approximately 42 degrees. So if I shine a ray of light at 45 degrees, the ray of light would totally internally reflect, like in this case. It's totally internally reflecting, right? And the same could be achieved with other triangular prisms as well. And what's interesting is this method of reflection totally reflects light, and therefore this is the preferred method for reflecting light, for example in binoculars and microscopes. Anyways, with that we wind up, and thanks for watching.